Some of the instruments in our range feature a very wide selection of alarms and additional features, but there are two basic types available on almost every model. These are the process high and the process low alarm. In the most basic form, they are very simple in their operation. A high alarm set at 100 degrees C, for example, would activate as the process passed that point on the way up, and if the temperature was to drop back below, it would deactivate again at probably 99.9 degrees C. In our Cal product range, this type of alarm is referred to as a full-scale alarm. It is available on all instrument types, including indicators, controllers, and the more specialist types of controllers such as profilers and limit controllers. In addition, most of the controllers will also feature a deviation alarm or a band alarm that works relative to the set point rather than to an absolute value. These control deviation error alarms activate whenever the controller is not able to maintain the process at or very close to the set point. If the set point is moved, the alarm has to move with it, so the alarm value is entered as an amount relative to the set point above or below which it must activate. For example, if the set point was set to 200 and a high deviation alarm was set at 5 degrees, it would activate at 205 degrees. A low deviation alarm with a value of perhaps -3 would activate at 197 degrees. If the set point was changed to 220 degrees, the activation points would be 225 and 217 degrees respectively. So you can use a deviation alarm to warn you if your process is getting too high or if it's getting too low. But what if you wanted to know if it was too high or too low? If your controller has more than one alarm available, you can set one up as a deviation high alarm and the other as a deviation low alarm, so that you'll receive a warning if there is a problem in either direction. If, as in the example I just gave, you wanted alarms at 225 degrees and 217 degrees with a set point at 220, this is exactly what you would do. However, if you want an alarm that is symmetrical around the set point, perhaps 5 degrees above and 5 degrees below, there is another option. This is the band alarm. You set a single alarm with a single value, and the alarm will activate if the process is that amount above or below the set point. The advantage of this is you use only one alarm and it's much simpler to set up. The uses for these alarms are almost endless. It really depends what is important for you in your process. Deviation and band alarms are used to draw your attention if the controller is not able to keep the process within the boundaries that you have set. Another example is the use of two process high alarms, one to shut the process down when an excessively high temperature is reached, and the other to act as a pre-warn below that point. The pre-warn allows the user to take some action to prevent the final high alarm from shutting the process down. The term alarm implies that there is some kind of problem with the process, but they can equally be used to signal some kind of information about the process state. In fact, with our PMA brand of controllers, they are quite often referred to as limits rather than alarms for this very reason. Another application for alarms is their use in multi-stage heating. In this application, successive banks of heaters are switched on as the process falls further below the set point. Or perhaps you want to stir your process as it's heated to ensure it's well mixed and there is a uniform temperature throughout. However, if your process was viscous and thick when it was cold, attempting to stir it below a certain temperature may cause damage to the stirring mechanism. By connecting the stirrer to a low alarm, you can ensure that the process is at the correct temperature before the stirring begins. Some of the models in our range have additional settings that we can use in conjunction with these alarms to tailor them more closely to our needs. First, we'll look at alarm hysteresis. Most of our models offer an adjustable hysteresis parameter for use with these alarms. This allows the user to define how far back below the alarm point the process has to move before the alarm will actually deactivate. For example, a high alarm set at 50 with a hysteresis value of 2 will alarm as the process rises above 50, but on the way back down will not deactivate until it reaches 48 or lower. The alarm hysteresis is always located on what is known as the safe side of the alarm. So, for example, with a low alarm at 50, the hysteresis of 2 would cause the alarm to deactivate as the process rose above 52. The use of hysteresis is normally associated with the use of an alarm as a signaller rather than a pure warning. For example, if you wanted a damper to open as the process reached a certain temperature, you would probably not want it to close again just because the temperature dropped 0.1 of a degree lower than the alarm point. This is where hysteresis is useful. It must be remembered that even on products that do not have an adjustable alarm hysteresis, the minimum amount of hysteresis must always be applied to the alarm, and this is usually set at one least significant display digit, so normally 1 degree or 0.1 of a degree. Another useful feature found on some of our instruments is the adjustable alarm delay timer. With this, when the alarm value is reached, instead of the alarm activating immediately, instead a timer is started. Only if the alarm condition has been present for the entire duration of the alarm time set does the alarm actually activate. This can be used to prevent nuisance alarms caused by momentary disturbances in the process. Another example of its use is to prevent a product from being drawn off from a process unless it has been at a certain temperature for a certain amount of time. This might be because the process has a temperature-dependent chemical reaction that can only take place after the correct temperature has been reached. When setting up an output to work with one of these alarms, it is important to consider whether to set that output up to be reverse or direct acting. If you previously set up a control output, you would already have come across the terms reverse and direct acting, and with alarms they do work in a very similar way. A direct acting output is on whenever the alarm is in the active state and off when it is inactive. A reverse acting output is simply the opposite. When the alarm is active, the output is off, and when the alarm is inactive, the output is on. An example of where a reverse acting alarm output may be useful is if we had wired a siren to the reverse acting alarm output on a temperature controller. If we had made the process fail safe by wiring the siren to the normally closed contacts of an alarm relay output, reverse acting would be needed. This is because we need the relay to be de-energized when the alarm is active and energized when the alarm is not active. Most of our products allow an alarm output to be latched so that it remains on even when the alarm state has passed. A typical example of where this is useful is if a high alarm has been used to shut a process down when it becomes over temperature. Without a latch, as soon as the process fell back below the alarm level, the process would be allowed to continue. Under these circumstances, that alarm output would effectively become the controller, activating as the process goes above temperature and deactivating as it falls below. To prevent this undesirable effect, we apply a latch to the alarm, and as soon as it goes above the temperature, the alarm will activate, and it will remain in that state even when the temperature falls below. Therefore, the process cannot continue until an operator has come across and solved the problem that caused the over temperature in the first place. Once the problem has been solved, the user resets the latched output and the process can continue as normal. Finally, we'll look at logical combinations of alarms. This is simply the linking of two alarms to a single output, or in some cases, one alarm and perhaps a profile event to a single output. These can be logical ORs, where any of the linked alarms will cause the output to activate, or they can be logical AND, where all of the alarms have to be active before the output will change state. Earlier, I gave an example where an alarm was required 5 degrees above and 3 degrees below the set point. In that case, I said that 2 deviation alarms had to be used. However, if we use a combinational OR alarm, we can at least use just one output to achieve what we need.